So essentially, normally when you're doing a chemical equation, you don't have the atom types being shown as, circles, ovals, and whatever else. So we're going to get rid of those to simplify the representation. So one CH4 that we've got here is equivalent to what I've got drawn here. 1 and then CH4 in the brackets. So it's telling us that we've got one lot of our CH4, which is methane. And the other reactant is two lots of O2. So you can see how we've simplified that representation. What was in the box is now inside the bracket, and the number out the front here is telling us how many lots of that molecule we've got. So in this case, we've got one molecule of CH4 and two molecules of O2, which corresponds to what we can see graphically up the top here. And what about the product side? Well, to go to the product side, we've now changed our reactants, so we represent that as an arrow showing that the chemical reaction has taken place. So the first product is CO2, and we have one of those. So notice that we don't write the 1, so we don't have C1O2. So if it's one, if an atom type has one lot of that atom, we don't actually write the 1. You just presume it's 1 if there's no number written. If you want to practice writing the 1s in, feel free to do that, but by convention, if it's 1, there's just no number shown. So similar to what we have here in the CH4, the 1 wasn't written there, so it was just CH4. So the C by itself just shows you that there's one of those. So going back to our CO2, there's only one lot of those, so we've got a 1 out the front there telling us that there's one molecule of CO2. And the last one there is our H2O. So the H2O is the molecule with this ratio of atoms, 2 hydrogens and 1 oxygen. And because we've got two lots of the H2O molecule, we have a 2 out the front. So just like we don't write the 1s to dictate the number of carbon atoms, for example, here, if there's only one of them, we don't actually show the 1 in front of the molecule either. So for example, if there's one CH4, you just write CH4 because it's presumed that there's one of them if you don't specify how many there are. Whereas for the oxygen, now that we've removed the brackets, we write it as 2 lots of O2. So when you have a number out the front here, it basically tells you that you've got 2 lots of everything that comes after the 2. So 2 lots of O2, which is what we have up the top here. So here's one O2, and here is a second O2. So that summarizes, this is summarized by the 2 O2 here. This 2 is telling you that you've got 2 different components, 2 of the same component here, and the O2 tells you what that component's made up of. In this case, 2 oxygen atoms. Again, for carbon dioxide, there's only one of those, so we take away that 1 and just show it as CO2, presuming that that means there is only one. And for H2O, we've got 2 separate H2O molecules, so there's 2 lots of everything that comes after the 2, which is the H2O molecule, which we see here. So it's very similar to the representation I showed you above here. We've just taken away the brackets, and if there's only one lot of that molecule, we don't write the 1. So you can see how our chemical reaction here can actually be more simply written as the chemical equation below. So it's very key that we understand what the different numbers mean in the chemical equation. If you have a number in front of a molecule, that tells you how many lots of that molecule there are. For example, the 2 in front of the O2 here tells you that there's 2 lots of the O2. And then we have the smaller 2 after, for example, these oxygens and after this hydrogen, which tells you the number of that type of atom in the molecule. So it's easy to get confused by which numbers mean what, so make sure you get your head around that. We've also got a few more slides coming up that talks you through this in a little bit more detail. Alright, so just a little bit of a flow chart here about chemical equations. So what we're looking at today is the non-reversible chemical equations, where we're summarizing a non-reversible chemical reaction, and that means the arrow only goes in one direction. So you go from reactants to products, and that's the only direction you can go. So left to right, traditionally it's written in. But as we'll see in later sessions, some chemical reactions are what we call reversible. So in this case, we have arrows going from left to right and from right to left, indicating that you can go from reactants to product, but the product can also be broken back down into the reactants. So a key thing about chemical equations is that the chemical equation has to be balanced. So this is because in a chemical equation, all you're doing is rearranging the existing atoms. You're not creating or destroying any atoms, just moving them around. So for every different type of atom present on the reactant side, there has to be the same number of each of those atoms on the product side. And that's what we're going to be having a look at when I show you how to balance the equations. So a little bit more detail now on why we have to have the same number of each type of atom on the reactant and product side. Basically, it comes down to the law of conservation of matter. So we've touched on this before, the fact that atoms are not created or destroyed in a chemical reaction, or really ever. They're only going to be rearranged. So essentially, this tells us that the point here in red, which is that the reactant atoms on the left-hand side of the arrow must equal the number and type of atoms present on the product. Okay? So we can see here in that chemical reaction that I was showing you that we've got the same atom types on each side of the equation, and if we add each number, if we count each type of atom on each side, it will actually be balanced. So we'll have the same number of carbon atoms on each side of the equation, same number of hydrogens, and also same number of oxygen atoms. And I'll show you how to do this in the coming slides. So a couple of other points to consider here is that when the reactants are converted into the products, you're not creating or destroying any atoms. So because all you're doing is rearranging, nothing new is created and nothing is destroyed either. So it's just a simple rearrangement. So in your own mind, what do you think is the reason why the atoms on each side of the equation, reactants and products, have to be equal? Basically, it's because we can't create any new atoms. So whatever you start with has to be equivalent to what you end up with in terms of the number of each type of atom. So you can't create an oxygen atom. So the only way to get an oxygen atom in a product is to get it from your reactant. So essentially, because we know atoms can't be created or destroyed, we just have to rearrange the existing atoms in the reactants to create new products. And that's the basis of what happens in a chemical reaction. Alright, so let's cover off on a little bit more detail in how to actually write our molecules within a chemical equation, either on the reactant or product side. We write it in the same way. So we call this form, when we have it in H2O, like this, the simplified representation, we call that the chemical formula of the molecule. So the chemical formula of the molecule tells you the number of each type of atom that is present in that molecule. So based on our H2O here, we can work out how many hydrogen atoms there are and also how many oxygen atoms there are. So because it says there's H2 here, that basically means that there's 2 hydrogens. And with the oxygen here, that is equivalent to there being 1 oxygen. We don't usually write the 1 because it's just presumed. So essentially, if we draw out the structure of water, we know that it's going to have 1 oxygen and 2 hydrogens. So it's more simply summarized as H2O. So the number after the atom type, for example, this 2, corresponds to the atom type that it comes after. So the 2 tells us that we've got 2 hydrogens, and the lack of a number after the oxygen tells us that we've got 1 of those in each of those water molecules. So to work out how many of each type of atom we have in the number of molecules present, basically we times each atom type by the number of molecules. So in the case that we saw in here, we've got 1 oxygen molecule, 1 water molecule. So that means we would times the number of each. So let's work out how many of each atom type we have in a water molecule by using this method here. So because we've got a 1 water molecule, we can represent it as having a 1 in front of the water. Normally we don't draw it if it's a 1, it's only 2 or higher, but for this example we've got a 1. So basically what we do is we times each atom type by the number out the front here, which we call the coefficient. So 1 times 2 hydrogen atoms, and then also 1 times 1 oxygen atom. So to work out the number of hydrogen atoms, we do 1, which is the coefficient, the number of water molecules, times the number of hydrogen atoms within 1 water molecule, which we know is 2 due to the H2. So that tells us that 1 times 2 hydrogen atoms gives us 2 hydrogen atoms in that 1 molecule of water. What about oxygen atoms? Well, there's 1 oxygen atom in each water, and we've got 1 molecule. So we do 1 times 1 equals 1. So essentially that tells us that in 1 water molecule, we've got 2 hydrogen atoms and 1 oxygen. What about though if we had 3 water molecules? So now instead of having just a single water molecule, we've got 3 of them. So this corresponds to having a coefficient of 3. So we can see we've got a 3 out the front of the H2O, dictating that there's 3 separate water molecules. So you could just physically count the number of oxygen and hydrogen atoms from this representation in the box, but there's a quicker way to do it. We're using the exact same method as I showed you above, where you times the number of each atom type by the coefficient here. So it'll be 3 times the number of hydrogen atoms and also 3 times the number of oxygen atoms. So for hydrogen, that will be 3 times 2, because every water molecule has 2 hydrogens. So in total, there'll be actually 6 hydrogen atoms within those 3 molecules of water. 2 times 3 is 6. And for oxygen, we do the same method. We're timesing it by 3 because there's 3 water molecules, and in each water molecule we've got 1 single oxygen. So that corresponds to 3 oxygen atoms within those 3 molecules of water. So we're going to need to be able to do these types of exercises when we're working out whether a chemical equation is balanced. So we need to be able to realize that when we've got 3 lots of H2O, this means we would have 6 hydrogen atoms and 3 oxygen atoms. So essentially it's just timesing the coefficient, in this case 3, by both the number of oxygen atoms and the number of hydrogen atoms. So we call the number that is after an atom type the subscript. So the subscript will basically tell you the number of atoms of that particular element that are present in the molecule. So for example, the 4 after the hydrogen here tells us that there's 4 hydrogen atoms within the CH4 molecule. In O2, it's telling us that there are 2 oxygens within the oxygen molecule. Remember, we don't draw the ones in, but in theory, if you wanted to, you could. So the subscript of this carbon here would be 1. So that's telling us that there's 1 carbon atom within CO2. Interestingly though, the subscript only affects the atom type that the subscript comes after. So basically that means that this 2 only affects the hydrogen. It does not have any effect on the oxygen. Okay? So you need to be sure of which atom type the subscript actually corresponds to. So, for example, this 2 here doesn't indicate that there's going to be 2 oxygens. No. It indicates that there's going to be 2 hydrogens because it comes directly after the hydrogen. So just be aware of that, trying to realize which subscript corresponds to which atom type. So it will always be on the right of the atom symbol in the molecule formula. Interestingly though, the subscript can never change in a chemical reaction. So when we move on to the next exercise where we're looking at how to balance chemical equations, we can't do it by changing these subscripts. Because if you change the subscript, you actually change the identity of your molecule. So for example, if we change O2 to O3, it's no longer the oxygen molecule, it's now a compound that we call ozone. Okay? So under no circumstances do we ever change these subscripts. Because if we did that, you'd be completely changing what you're writing and representing in your chemical equation. It would make it completely different. So you can think of these subscripts as fixed and unchanging. And as I've been saying, the subscript of 1 is not shown. So instead of writing it methane as C1H4, we simplify that as being written as CH4. So without the 1 there, you just presume that the atom type has 1 of those atoms within that molecule. Alright, so let's look at another example here to put this subscript interpretation to the test. So this is ethanol, which is a compound present in alcoholic beverages. So we've got 3 different atom types within this one compound. We've got carbons, hydrogens, and oxygens. So your challenge is to work out how many carbons, how many hydrogens, and how many oxygens are present within this compound. So I'll give you a little bit of time to have a go at that. So essentially the first thing to recognize is that each atom type is arranged in this way. So the 2 after the carbon corresponds to the number of carbon atoms, the 6 after the hydrogen corresponds to the number of hydrogen atoms, and the no number after the oxygen tells us that there's 1 of those. So within our compound here, we've got 2 carbons, as shown by the C2. We've got 6 hydrogens, as shown by the H6, and we've got 1 single oxygen, as shown by the oxygen without a number there. If you wanted to, you could put that a 1 there. So the other key number in these chemical equations is the number that can be shown in front of a molecule. And as I've already told you, we call this a coefficient. So basically what the coefficient does is it identifies the number of molecules that are present in the chemical equation for that particular type of molecule. So remember, a molecule where there's just 1 of it, we don't usually write the 1, but in theory you could put a 1 in front of the CH4 and also the CH2. So we always have the coefficient written in front of the molecule, whereas the subscript that we saw in the previous slide is always coming after each atom type. Okay, so that's the difference between the coefficient coefficient in front of the molecule, and then the subscript is actually within the molecule. So the coefficient is actually what we can change when we're attempting to balance chemical equations. So when I show you how to balance chemical equations, to make sure it's balanced, we're actually going to have to adjust these numbers out the front of some of these molecules to actually mean that we have the same number of each atom type on the reactant side as we have on the product side. So what does the coefficient actually do? So basically it tells you that you've got two of those molecules. So if we take the example of H2O, H2O has a 2 in front of it. So the 2 in front of H2O means that there's two separate H2O molecules. So that corresponds to two lots of our H2O, like this. So we can summarize two lots of H2O as having a 2 in front of our H2O, because the coefficient is telling us that we've got two lots of this whole molecule here. What about if we had a coefficient, representation like this? It was 8 CO2. What does 8 CO2 tell us about how many units of carbon dioxide molecules we have? So if you remember, CO2 represents carbon dioxide, so we can get the information about how many of these compounds we have from the coefficient out the front here. So because there's an 8 in front of the CO2, that tells us that there's 8 lots of our CO2 compound. So I'm not going to draw them all out, but essentially the 8 will tell you that you have 8 of everything after that, and that is the CO2 molecule. So whatever the number is in front of the molecule, that tells you how many of that molecule type there are. What about if we put 100 in front of H2O, like that? So the coefficient is now 100. How many molecules of water would 100 H2O represent there? That would mean you've got 100 water molecules. So just keep that in mind. If you've got a number out the front of a molecule, it tells you how many of that type of molecule there are. And if you've got a number within the molecule, the subscript, it tells you how many of that atom type are present in that particular molecule. And we always have the coefficient being a whole number. So you can't have 0.502, for example. It has to be 1 or higher. And as I was saying earlier, we don't normally write the coefficient if it's a 1. So instead of writing 1 CH4 to represent one CH4 molecule, we just write it as CH4 for simplicity. Okay, so now that we've been through in detail this example of a chemical equation and chemical reaction and how to represent that chemical reaction as the chemical equation, now need you to have a go at this exercise, which is to identify the coefficients and subscripts in the below chemical equation. So you can do that from this simplified representation down the bottom here. So put a circle around each number and specify whether that number represents a coefficient or a subscript. It's probably also worth saying what a coefficient is and what it does, as well as a subscript. So basically a definition for coefficient and subscript, and which ones are actually coefficients and subscripts within our chemical equation down the bottom here. So now would be a great time to pause the video and have a go at this exercise. Okay, so let's work from left to right here. So in the first molecule, we've got one number here, which is a subscript. So that subscript tells us that there's 4 hydrogen atoms within our CH4 molecule. The next number we encounter is a 2 in front of our oxygen. So this 2 is actually a coefficient, telling us the number of oxygen molecules present. So we've got 2 lots of the oxygen molecule present, and each molecule contains 2 oxygen atoms, as shown by this subscript here of 2. There's also 2 oxygen atoms within the CO2 molecule, so we've got another subscript there. The coefficient of 2 out the front of the H2O, what does that tell you? Well, it tells you that you've got 2 lots of H2O, and within that H2O, there's going to be 2 hydrogen atoms in each one of those. And for all these atoms where there was no subscript, we just say that there's one of these. So there's 1 carbon in CH4, 1 in CO2, and 1 in each water molecule. So remember, the coefficient is basically the number that tells you how many lots of that particular molecule are present, and the subscript is the number that tells you the number of atoms of that particular type present in a molecule.